start with a little bit of logistics. So there will be a graduate student tea today at 4 o'clock in the usual little second floor Atlantic conference room. So students and postdocs, you should really consider going. This is a chance to ask David some questions without us faculty monopolizing the conversation. So this is really a good opportunity. As usual, we have our seminar running on hybrid. If you are on Zoom, please do not use the chat. And you have a question, please just speak up. We will not be monitoring the chat. So if you put it there, we will not answer it. Just please speak up and we will do our best to repeat questions for the Zoom audience. I think also I want to make a request of the in-person folks. We've had a lot of really lively discussions the last couple of weeks, which have been great, but many speakers have only gotten about halfway through their talk. And so I would like you to consider that if your question might be on the speaker's next slide, please hold it and see if it comes up.
Are you referring to anyone?
No. I also want to say, like, some of these questions have been really, really good, but maybe some of them are better reserved for lunch or after the talk. Some of the students have actually requested that maybe we go on slightly smaller digressions because it makes it a little harder for them to follow the flow of the talk. And so that doesn't mean don't ask a question, but just be a little bit considerate, please, of everyone else in the audience and the level of specificity at which they are watching the talk. You know, we'd like to have good discussions, but also we'd like to see the end of talks too. Okay, and so with that, I'm very excited to introduce David Weld as our speaker today. He's come all the way from UC Santa Barbara to talk to us. So David is very well known in ultracold atoms, particularly for working with driven ultracold atom systems. I tried to be as minimally embarrassing as possible. And so he was a Harvard undergrad, a Stanford graduate student, and an MIT postdoc. And now he does amazing things at Santa Barbara. And I will let him tell you about them instead of awkwardly paraphrasing.
Thank you so much for the kind introduction. And thank you all for coming. And I don't want to countermand the instructions just given, but I'm from Boston, so I can talk very fast if I need to. So if we have a lot of questions in the first half of the talk, I'll be very happy and can really whip through that second half.
You should be aware of that opening salvo with this.
Okay, yeah, I have some familiarity. So anyway, I hope that we can get a good discussion going both in person and on Zoom. Okay, so yeah, I guess the title of my talk is Probing Quantum Dynamics with Strongly Driven Ultracold Atoms. And that describes a variety of work that we've been looking at recently in Santa Barbara, including a set of experiments where I would say we are exploring localization physics in various forms. And then a new direction that I want to talk about at the end of the talk, if there's time, which is this idea of quantum interactive dynamics. And that next part is an experiment that's under construction and just some ideas. And so the first part of the talk is the one that actually has real data in it. So we've done a couple recent experiments on this general theme of exploring localization. And I'm not going to talk about all of these. Obviously, this is much more than a seminar. So I'll just mention these red ones that I'm not going to talk about. The first one is a study of what you might call many-body delocalization, done together with Victor, who's here, in a quantum kicked rotor that we introduced interactions to. After that, we explored something called the quantum boomerang effect, which is surprisingly a dynamical phenomenon intrinsic to Anderson insulators that hadn't really been thought about even theoretically until a couple of years ago, that we were able to do some experiments on. And then finally, a paper that could be considered to be a step in the direction of quantum interactive dynamics, looking at what happens if you make a thermodynamic engine with a Bose condensed working fluid. So those are just sort of advertisements. I'm not going to talk about those. What I'm going to focus on is a sequence of experiments, really, I would say, looking at the interplay between dynamics and localization driven by disorder, or something that is a reasonable facsimile of disorder. And then at the end, this idea of quantum interactive dynamics, which we're building a potassium tweezer Bose condensate experiment to try to explore. And I'll talk a little bit about what some of the vague scientific goals are for this apparatus. Okay, so boiling down the outline to what I'll actually talk about. The first bit of work I want to discuss concerns anomalous localization in a kicked quasicrystal. And then I'll talk about some generalizations in that same system. What happens if you drive what are called phasonic degrees of freedom in the quasicrystal, and what happens in the interplay between different forms of localization. So just a quick background here. For those of you who are not sort of super familiar with localization physics in general, it's been known for quite a long time, since the 50s, that disorder can drive a transition between a metal and an insulator, right? Everything that's not a metal needs an excuse for not being a metal, and one of the excuses is disorder. And it doesn't have to be true disorder, as considered by Phil Anderson in that top paper. It can be quasi-periodic disorder. So these other two papers, one is by Aubry and Andre, and one is this famous Harper model that connects the physics of one-dimensional quasicrystals to two-dimensional electron gases in high magnetic fields. So this is a very well-studied topic. All of these papers that I put the abstracts of here have more than 1,000 citations, many more in the first case, and many of you will be very familiar with it. So I want to try to say hopefully a few new things. And the main experimental tool that we use in this work is driven quantum gases. So down at the bottom of the slide, you can see, or actually, yeah, it comes up pretty good on this projector. You can see a sequence of images of a degenerate quantum gas of strontium atoms that are being subjected to increasingly strong levels of disorder. And you can see that if there's not much disorder, they spread out. This is after some hold time. And if there's a lot of disorder, they don't spread out. And that's the basic kind of measurement that we do to see, to try to diagnose the physics of localization, is really how much do things go away from where you put them. Okay, so I want to now introduce a Hamiltonian that underlies a lot of what I want to talk about today. And this is the Aubry-Andre Harper model. And it's a relatively simple Hamiltonian. It's just got two terms in it, really. A hopping term, so this J A dagger I AI plus 1 is telling you, the particles can hop from one tight binding site to the next. And it has some incommensurate modulation of the chemical potential. That's this lambda term, where that number alpha controls the ratio between the underlying lattice and the period of the quasi-disorder. So this is maybe the simplest prototype that I know of real space quasi-disorder driven localization phase transitions. And you can, let me say three things about it. One is you can realize this very simply in a cold atom experiment, as many people have done, using just two optical lattices with different spatial frequencies. And you can consider that to be a model of a one-dimensional quasicrystal. Quasicrystal is an object that has no translation symmetry, but no disorder. And that's what this is if alpha is an irrational number. Or you can think of it actually as modeling the exact energy spectrum of integer quantum Hall states of two-dimensional electron gases in large magnetic fields. And that's a relatively well-studied model, including references that I put down there and a lot of references in between them. And the new ingredient that I want to talk about in the first section of my talk today is what happens if you add this delta function term to that Hamiltonian, which is to say that you turn on and off the quasi-disorder. So what we have here is, like, in some ways even simpler. Almost all the time, it's just a plain lattice, nothing else, a plain one-dimensional tight binding lattice. But every once in a while, we pulse on this incommensurate quasi-disorder term. That's what this delta function is telling us. And we want to see what happens. First question you might ask is, will it localize? Most of the time, this is just a 1D system that has bands. It's going to be a metal. So can localization occur in this system, which is periodic almost all the time, except during these delta function kicks? I do want to note, because it makes some nice connection to the work we did with Victor, that another way to look at this is as another kicked rotor, where you have, with a kicked rotor, you have a Hamiltonian that looks like this, just some quadratic kinetic energy and some kicking term that's times a cosine. But here, instead in the kicked rotor, you've replaced the quadratic kinetic energy by a band structure. That's kind of coming at this kicked Aubry-Andre Harper model from a different direction, but getting to the same place.
So you could imagine going just a little bit further
Mm-hmm.
and just always have the the quasicrystal on and kicking it.
Shaking it?
No, kicking it. That is turning it, turning it on much more strongly.
Yeah, that's true.
Is that something that
Um,
has any?
That's an interesting thought. I don't think we've done that experimentally. We have done a different kind of kicking, which I think I'll show a little bit of data on, where you have the quasicrystal always on, and you shake the whole system, or modulate what I'll call the phasonic degree of freedom. But going from non-zero to stronger disorder, we haven't really looked at. I don't know what I'd expect there. It's an interesting thought. Guess it would be like a kicked rotor, but with a more complicated band structure. Yeah.
It's natural anyway.
Yeah, no, I see what you mean. That's an interesting way to think about it. Okay, so the question of what happens has been explored a bit theoretically, and it's pretty easy to see what happens in the limit where this parameter big T is small. So that's the limit of very rapid kicking. So what you might expect happens in that scenario is it kind of averages out, and you have some effective quasi-periodic strength, which is like, based on the duty cycle of this thing and how large the pulses are, the parameter lambda. So in that regime, indeed, what you see is an ordinary Aubry-Andre transition, where as you increase lambda, the strength of the disorder, sorry for the change in capitalization of lambda, you go from something that looks metallic to something that looks insulating, and where that transition happens depends on the period linearly, because the duty cycle depends on that. So this is, I would say, something that looks just a lot like the static Aubry-Andre Harper model. And there is retained, even in this kicked model, the duality that maybe specialists among you will be familiar with in the Aubry-Andre Harper model. There's some momentum position duality between the localized and delocalized sides of this transition, which pins the transition to be at one particular value of twice the tunneling matrix element. That's still true in this kicked model. And right at the transition, you have a critical state. Yeah.
So, it's really a stupid question. It doesn't matter. It looks like how one over T and how lambda compared to J, like somehow.
It does matter. It does matter. That's one of these questions that's on my next slide.
Because from the plot, it doesn't seem like it, right?
Because these are not getting very big so far. I'm going to show another plot with expanded X and Y axes. Yes, but you've put your finger on exactly the key point here. So this plot is in the small t limit, and it's looks like this, but you'll see that exactly as you'd expect, it blossoms out in an interesting way. So why does that happen? Oh, yeah, in the back.
Is this true for long time or is this thermal?
Yeah, good question. I realize I've been forgetting to repeat the in-person questions. Is this true for long times, or is it a pre-thermal phenomenon? We are largely neglecting interactions here. Once you include interactions, surely this is a pre-thermal phenomenon. But I mean, our atoms do interact, but we don't have very large densities, so it's something we can largely ignore. And we've done elaborate checks of that statement. Okay, so yeah, why, as Alexei points out, why would increasing the kicking period lead to something different? It does, and it's because, if the atoms have time to hop in between your kicks, then something different is happening at kick number 2 than was happening at kick number 1. So as t gets comparable to the hopping time, you can think of this as some effective further off diagonal terms in your Aubry-Andre Harper model, which is sometimes called a generalized Aubry-Andre Harper model. And that kind of thing has been investigated theoretically quite a lot and is broadly known to stabilize interesting states where the wave functions have critical multifractal character. So I've drawn some results of calculations done by one of my postdocs here. An extended state looks kind of extended like this. These are in position space. A localized state looks localized. It's almost like a delta function, or at least an exponentially localized thing. And a fractal state actually has real fractal self-similarity on multiple scales, and some fractal dimension, or possibly even multiple fractal dimensions. And these are the kind of things you generally would expect to see only at a critical phase transition. And it's a generally reasonably theoretically well-known thing that these higher off diagonal matrix elements can stabilize fractal states like this. So you can explore going to larger values of t and lambda, the phase diagram of this model as a function of the kick period t and the quasi-disorder strength. And so now see here, we're going out to values of t up to 4 times the tunneling and, commensurately large values of lambda. And then you see a much more interesting phase diagram where it's not just this linear Aubry-Andre Harper transition, but something more complicated. Yeah, Victor.
Reflects about this phase diagram business. So in the usual peak models, we're talking about time-dependent problem where actually localization appears in momentum space. There is a dynamic localization.
Yeah.
So here you're talking about some time-independent sort of phase diagram. So I can't really reconcile this.
So this is like what's being plotted here is a position space diagnostic of localization. So I should say the color bar on this plot is just like, it says sigma x over sigma naught. That means like how wide did the distribution get after some time in units of how wide it was when you put it in there. So how much do things spread out in position space here?
Yeah, but then there is another metric basically. Do you kind of impart energy into the system? So is there something like energy as a function of time where you just do time of flight and just sum over mv squared over 2 kind of thing? So because that's what's done in the usual kicked rotor.
Coming from the kicked rotor side, yeah, I see what you mean. Well, I guess I think the change from the quadratic kinetic energy to the band sinusoidal kinetic energy here makes some sort of fundamental difference, where the localization looks like it's driven by disorder in a position space lattice instead of disorder in a momentum space lattice. That's at least how I think about this. Does that make sense?
Well, maybe we should postpone the next one, but I mean, the hopping on a lattice has a limit, which is p squared over 2m, right? So I mean, if I'm if I expand near the bottom of the band, well, then it should be actually equivalent.
Yes, that's true.
So there is some limit where it should be equivalent.
Although I think our system here should be exploring the whole band, most likely. So I think it's probably not close to that limit. But yeah, it's interesting. I mean, this is really, there's all over these, both in the kicked rotor and the Aubry-Andre model, there's these interesting dualities between position and momentum space. And I think what Victor is pointing out is like a version of one of those.
So is it obvious that this ratio is independent of sigma naught?
Good question. Is it obvious the ratio is independent of sigma naught? No, I think a theoretically more well-motivated thing to plot, which we've also plotted a lot, I can't remember if it's in my slides, is like an IPR, an inverse participation ratio. And if you plot that, you see, a broadly similar phase diagram. It's a little more plain in that case that there is a duality across this line, which actually still persists. What I'm plotting here is something very experimentally motivated.
The IPR, you can measure the IPR as well.
It's a little hard to measure the IPR, and truthfully, but it's theoretically very well understood and can be accessed very well numerically. And so maybe a crisp answer to your question is we've checked numerically what the initial state dependence is. And there is some, but not like qualitative.
So stupid question. So the eigenstates you're plotting, are these eigenstates of the unitary over one time period?
Are they Fouquet eigenstates?
Is that what you're plotting?
Yeah. Good point. Was there one more question? Oh, that question was, are these Fouquet eigenstates? And the answer is yes.
So going back to what Jay asked, does this diagram then imply a certain limit on what sigma naught is? And what is that?
I see. No, I mean, this diagram is really experimentally motivated. I think only in my extra slides do I have one of the IPR plots, which are very beautiful. But I don't think it implies any limit on sigma naught. I mean, our sigma naught experimentally is limited by, just the size of the Bose condensate that we load into this rather large lattice. You can start with if you load a single site, you still see the same thing. And there's actually maybe, I don't know, this is one of the digressions that I was warned against, I suppose, but if you load multiple sites, actually the coherence properties among those sites makes a difference to the early time dynamics, but not to the late time dynamics. So this is one of the actually key subtleties that we untangled. By the way, in close collaboration with our theory collaborators, Tarun Grover and Peter Liu, who are shown here, who I want to really give credit to for our understanding data that mystified us for months and years, actually, before we got together with them.
So this is the late time.
Yeah, this is reasonably late time, at least. We have like 15 or 20 pages of supplementary info in the paper on this, which goes into detail on these features. there's actually some pretty interesting details. Let's see if there's time to talk about them. But there's some funny subtleties there for sure. And then this right-hand plot, just to point it out, is showing the percentage of states that have fractal character, that have some fractal dimension that's not 0 and not 1. And for the Aubry-Andre model, you see these fractal states appear only right at the transition, which is typically what one expects. You expect to see funny critical phenomena occur only if you fine-tune to a phase transition. And here we see that for this large T, large lambda regime, given by the purple curve, actually this whole area in the middle of the phase diagram is generally characterized, we see numerically, and we see some evidence experimentally, by the presence of critical and multifractal type correlations across a broad range of parameter space.
This is, maybe you said this and I missed it. T is in units of what?
In units of the tunneling time.
The tunneling time.
Yeah. So for 4, that means you kick, and then the atoms have time to hop 4 sites before you kick again. And lambda is in units of the tunneling energy. And so this transition is at T, lambda equals 2T, which is the ordinary Aubry-Andre. 2J, which is the ordinary Aubry-Andre.
Follow-up question, then this delta function is proportional to 1 over T.
Which the delta function in the Hamiltonian? I see. So you have to think of this as having unit area, right? This is in an experiment. It doesn't really go up to infinity.
In the experiment has some width, and that is
Yes. And
much shorter than any time.
yes. Good point. Yeah. And then what we control is really the area of the pulses, and you can use larger, narrower pulses or shorter, fatter pulses. And as long as that time scale is short compared to everything else, it doesn't matter what you do. But yeah, good point. Right, one should be careful of delta functions in experiments. Okay, so getting to the experiments, the way we probe this model is with a quantum gas of strontium-84 in a static lattice made by an ordinary YAG laser, and then we pulse on another lattice, which is at an incommensurate, somewhat shorter wavelength, and we just observe the spread in position space along the lines of these data that I showed you before along the bottom of the slide. So what do we see? Well, the first thing to say is here's kind of what the data look like. So if you go to some regime of the phase diagram where things are delocalized, you see the atoms spreading out. This is a sequence of images at different times, up to 2 seconds of hold. They spread out nicely. And if you go to a more localized regime, they kind of don't spread out. So you can see that it's possible to just visually diagnose the presence of localization. It's also instructive, and I'll come back to this a bit later, to plot the functional form of the growth of the distribution in time. And that can be characterized by different exponents. And so we generally, if we plot out this phase diagram, you see as we increase T and increase lambda, we see, as predicted, and at the predicted point, this kick period dependent delocalization, localization transition as you increase lambda. So that's nice. The bad thing, there's 2 bad things here. One is that there's a lot of junk in the upper right of this plot. What those crosshatches mean are that I rejected data due to heating and transverse excitations, and that's just happening generically at the upper right of the plot. And the second bad thing is if you look at the axes here, these are the same units as before. I'm only actually getting up to kick periods of about 1% of the hopping time. So we're nowhere near the regime where I claim that anything interesting happens. Yeah.
How do you place this dashed line for the transition? Because it seems like there's no natural like 0 in your like merit of the expansion of this.
So it's just where the dashed line is where the disorder strength is equal to twice the the effective disorder strength, where you sort of normalize by the duty cycle of the kicking is equal to twice the hopping.
How do you put the white patch in your color bar? Right? Like why is that the transition in your sigma X as opposed to
how do you choose the color bar here?
what you by identifying that line, the transition in your data? Like you said, there's something in your merit that like has a district has some kind of change there.
Yeah, so you calibrate that with respect to a static Aubry-Andre model, where you can see such a phase transition sort of in a pretty boring and easy to diagnose way. And that's actually how that color bar was set. Yeah, good question.
And when you say it's not interesting, what you mean is it's just the Aubry-Andre.
I actually, yeah, you're right. When I say it's not interesting, I'm lying. I love the Aubry-Andre model. In fact, someone has made fun of me for this recently. I think it's a very beautiful and wonderful model. I take it back, Aubry-Andre. Yeah.
Sorry, maybe just to expand on that question. So it's, I guess maybe it's not so obvious that sigma x by itself can mark a transition in a singular sense, right? I mean,
yeah,
maybe as if you look at long times, the scaling with long times.
Yes, that's a very good point. And I think what gives you a little more information is looking at time evolution. That's a data cube, though. Like what I would like to do, I think it would be better strictly, would be to do that for every pixel of a phase diagram like this. But that's then like continuous data taking for a month or something like that. So we
we should view the below the dashed line as like the blue, qualitatively similar to the blue line in the middle block. And
yeah, exactly. Although we're really just picking out a single late time value for these phase diagrams for just reasons of data luminosity, I would say. Takes us about 25 seconds to just do one run of the experiment. And so that tends to add up once you do averaging. Okay, I just mentioned several bad things. Everything is terrible. We can't see the fun physics we want to see because our Fouquet engineering is fundamentally breaking down as we increase T and lambda. The atoms are heating like crazy. So is there anything we can do about that? It turns out there is, and it's like kind of a very old school thing to do. And I only mention it. Feels like an experimental detail, but I mention it because it works really well. So what we did is we have these kicking pulses, as one question already asked about. Like obviously these aren't really delta functions. They have some pulse shape. And that's a pulse shape that you have some control over. So you can do something that, 50 years ago in RF engineering or optics, people would have called apodization, and still today, I assume. And all that means in this context is to control the shape of those kicking pulses to minimize the power spectral density at naughty frequencies. So you can see here, well, this first graph is basically showing that we understand why the atoms are heating. It's because we're driving interband transitions. The second graph shows that if you use different pulse shapes, you can minimize the power, which is the y-axis here, at interband transitions. So these light purple regions you can barely see are places where you expect to excite higher bands, and you can kind of suppress those by pulse shaping, which you could do either simply by using a Gaussian or with some fancy numerically optimized, tried both. And the rest of the graphs really show that this works really well. So if you implement this kind of pulse shaping, you can drastically decrease the kind of heating you see and drastically increase the range of the phase diagram that you can access with your Fouquet engineering techniques. Realize I have no idea what time it is. I need to keep an eye. So it turns out that this just works really surprisingly well. And in fact, opens up 100,000 times larger phase diagram than the one that I showed here. So this is my crude animation. The phase diagram shrinks down. And now this is what we can access with these new apodized Fouquet engineering techniques. And now you can see that the kick period is kind of going up to the region that our theory was before, around 4 tunneling times. And we do indeed see some kind of non-trivial features in this phase diagram. So I want to point out specifically 2 features that I guess I forgot to highlight in the theory because of our good discussion, but which we see in both theory and experiment. So one is this idea of re-entrant delocalization. So if you go, somewhere around here in the middle of the phase diagram and increase lambda, there's an area where the system appears to make a transition from a localized state to a delocalized state with increasing disorder. That's a little bit exotic, and matches onto theoretical maps. And another thing is that you can study transport exponents across the middle of this phase diagram. And they're indicative, although I wouldn't say perfect proof, that there is this extended multifractal regime, which appears unambiguously in the numerics in the middle of this phase diagram. So the main result of this work, which is appears in the archive down there and was recently accepted to Nature Physics, is that we were able, using these apodization techniques to measure the phase diagram of the kicked Aubry-Andre Harper model. And this is a phase diagram that actually has a lot of richness to it, and I think maybe some opportunity for future study. The two features of it that I'm excited about from this work are the re-entrant localization transition and the indications that you're really generating some multifractal critical regime across a broad swath of the phase diagram, not only at a phase transition. Yeah.
Okay, cost engineering. I think there are two effects, if I understand correctly. One is that you want to suppress the transition to other bands.
Yes.
The other one is that you have this micro motion that you did not talk about. Like follow up to what Alexis said.
Interesting.
This is a locate system. So you just look at the integrated time of H over a cycle. And you don't care about the micro motion inside that. So when you're changing this pulse shape, you're actually changing that micro motion.
That's true. The question is about the pulse shape having an effect on the micromotion during the kicking. But I guess in relation to your previous question, if even for the engineered pulse shapes, all the timescales are short compared to what the atoms kind of can reasonably react kinetically to, then I think it's still.
But you know that they don't. So there are like two effects. Like I can have single band and this locating and the micromotion and also the transition.
I see what you're saying. So even in the absence, if we could sort of get rid of all the higher bands, would this still have an effect? Yeah, very interesting question. The answer is I don't know, but my suspicion is that it would be not anything that would change the sort of qualitative results here. Everything that we've seen, both in theory and in the experiment, really seems to depend on the pulse area and not too sternly on anything other than that one parameter. But it's a good point that phenomenon must be present at some level. Yeah.
Now, one of the banes of any floquet situation is interactions.
Yeah.
So you said you were ignoring interactions, but of course.
Yeah.
So what's the deal?
They're present. And it was the subject of a long, like more than a year long discussion with some reviewers. Okay. What we ended up doing, the question was about interactions for the Zoom audience. What we ended up doing was doing the experiment with different atom numbers and different levels of transverse confinement and looking at how the effect scaled with that, just to make sure we weren't looking at some interaction-driven phenomenon. And what we found was the interactions were indeed not super important. At the long times, as somebody pointed out, they must lead to heating. But even at these are pretty long times, actually, holds of up to 2 seconds. We found that it did not have a strong effect. Yeah, but it's obviously an important thing to check, especially when you're seeing some stuff like a little bit exotic looking phase diagrams like this. That's something you need to worry about. And it did take us quite some time to check that. Okay, so let's see. When should I aim to cease speaking?
I think around noon, especially given
Okay.
the front loading of questions.
Yeah. No problem. But feel free to tell me if I'm going on too long. So what I want to talk about now is just a few results building on this, using a similar model so we can use our same intuition. Before I pivot to a totally different topic of the quantum interactive dynamics at the end of the talk. So what I want to talk about here is, back to this Aubry-Andre Harper model, which we talked about already. Now we're going to forget about the kicking, just have a static Aubry-Andre Harper model. But now the time dependence is going to come via this added term here. So the incommensurate perturbation has a phase, unavoidably. And that phase is what you would call in a quasicrystal a phasonic degree of freedom, something that's a little bit analog of a phonon in a crystal, but happens in some higher dimensional space for a quasicrystal. And that's a thing that you can make time dependent. In particular, we can make it experimentally time dependent. And you might ask yourself what happens if you drive this parameter. And we did ask ourselves that and try a few things. Now let's see if the animations carry over. Okay, so you can imagine shaking a quasicrystal like this in at least 2 ways. One is, as shown in the cartoon just now, shake the whole thing back and forth. That's equivalent to some inertial oscillating electric field. And if you do that, you see a super simple spectral response where you deplete the ground band only if you shake it right at the band gap. That's what you're seeing here. If you instead do a phasonic modulation, where the parameter you modulate is the relative phase between the two sublattices, you actually see something pretty crazy. And this is something I'm not going to talk about actually too much, but it's discussed in this PRL, which is done together with Andre Eckhart and Egidius Anasimovos, our theory collaborators. And what we see basically is a very strong non-perturbative high harmonic response. That's not what I'm going to talk about. What I'm going to talk about is that same experiment, but in a much lower frequency regime. And when we first started doing this, the reason we started like slowly shaking the phasonic parameter was I figured that's going to destroy localization. There's no way that the delicate interference that stabilizes an Anderson localized like state is going to survive moving around that phase. So I figured this is a good way to show that we have Anderson localization, that we can kill it by doing this. And indeed, that's what we saw at first. So these data here show sort of increasing strength of the lambda parameter. And so you see localization happening here without any phasonic driving. And if you add some reasonable strength, slow phasonic driving, it doesn't really localize, or at least it doesn't localize as well. So it looks like, as I naively suspected, phasonic driving suppresses localization just kind of by scrambling stuff. All right, and that's my animation. That's a reminder of what I mean by phasonic driving.
Sorry, David, what does it mean? In your case, what's the?
I really am saying the atoms don't spread out. But in position space, you put them down and they stay there. So you're putting them, in some mixture of the eigenstates of the model. So presumably, if the eigenstates are all delocalized, they will move around like they would in a unperturbed single frequency lattice. So if they don't move around, I'm experimentally calling that a signature of localization.
Have you considered in many of these experiments just energy as a function of time? Oh,
yeah, it's a great question, because in our experiment that we worked on together, like in the kicked rotor, that's really the thing you want to look at. And here we have less good access to the momentum degrees of freedom because we let the system evolve for many seconds. So the position space, there's a large position space evolution, and the standard time of flight that you can do is kind of unavoidably convolved with that. Whereas the kicked rotor experiments all took less than a millisecond. So, 10 millisecond time of flight gives you a really nice picture of the kinetic energy. So in some ways, the tools we have experimentally are a little different here. But in other ways, I would say really what we're kind of thinking about and looking at here is position space localization.
Yeah, so but just again, I'm sorry, we're pulling up on this, but mathematically, that's kind of very similar model. I can still do the same one in the momentum space.
Yeah.
I could argue there will be momentum space localization.
Yeah.
Kind of interesting.
Yeah, I think
So
a number of these questions are connected, I think, and very interesting. What that's going to look like if there's delocalization in energy is higher band population. And we do see that, and that's actually connected to this sort of experimental apodization technique I talked about. So you can control that a little bit with the pulse shape. Yeah, okay, that's a very big topic. I think interactions are related to that as well. But I think what I would think of looking at to probe that kind of physics is more like the higher band population as a function of time, which is something we also see in some regimes here. Yeah, really, really, really good question. I think there's deep waters here in a variety of directions. Okay, so I'm saying I kind of turn on the phasonic driving and localization appears to be suppressed. But the reason I'm telling you this is it's a little more complicated than that, because what we see if I turn up the amplitude of that phasonic driving more and more and more and more and more is the system that initially went from localized to delocalized goes back to localized, delocalizes again, localizes again, and so on and so forth as a function of the amplitude of this phasonic driving. So this was like a genuine surprise to us. Yeah.
So, relative to the size of these clouds, how many lattice sites are in the cloud occupying?
Oh, hundreds, if especially in the more spread out one. Yeah, maybe at the smallest on these pictures, the smallest is probably 50 lattice sites, I would guess.
And then what's the amplitude in lattice sites? Are you?
Oh, big. Yeah. So, all right, that's volts. That's a very lab
Yeah.
unit. But I think, yeah, good point. It's a couple lattice constants across this graph, I think. So it's really a big phasonic modulation, which is, of course, crucial to understanding what's going on here. So if you kind of plot these results, the interesting thing you see is, well, up top, these are just pictures of atomic clouds. And you see as a function of shaking amplitude, now in the slightly more relevant unit of nanometers. So you can see there's a few lattice constants here. You see the sort of delocalization, localization, oscillation here. And the somewhat surprising thing is it doesn't depend at all on what frequency you drive the phasons. You drive them at 300 hertz, 600 hertz, 900 hertz, and you see the same overall structure, where you see peaks depending on the particular drive amplitude. And
always avoiding those bad frequencies. Is that right?
Good question. These frequencies are all in the sort of good Fouquet engineering regime, which is between the bandwidth and the band gap. So we're not, and this is also sinusoidal driving, so it's true monochromatic. So it's, yeah, we're avoiding for sure higher band excitations. So the key observation here, if you kind of plot this in reasonable units, as Bill suggested, instead of volts or something, but in terms of 1 over twice the wave vector of the secondary lattice, then you see that these delocalization peaks occur at zeros of the J0 Bessel function. And so that's maybe reminiscent for specialists of some of these works done quite a while ago on phase modulation of optical lattices, where you can renormalize tunneling to 0 by shaking, and it gets renormalized by a Bessel function. We're not doing the same thing here, but some of the same math is involved. And in particular, there's this Jacobi-Auger expansion where the what you have is kind of a cosine of a sine. This is just that term in the Hamiltonian with the sinusoidal phasonic drive, and that can be expanded. And the first term in the expansion is a J0 Bessel function multiplying the cosine. So you get this dynamical renormalization, not of the tunneling in this case, but of the strength of the quasi disorder, and it can go to 0 and go negative because that's what the Bessel function does. So this is fun because it gives us a tool for coherent control of localization. You might ask yourself if that's really what's going on, and I think this plot shows that it really is. What I've plotted here is a normalized measure of the inverse spreading. How big does it get compared to how big does it ever get, kind of, and that's as a function of the shaking amplitude. And then the red line here is actually not a fit at all. There's no fit parameters here. That's just the absolute value of an actual Bessel function. So you can see that the this parameter here, which turns out to be linearly proportional to the quasi disorder strength, which you can show numerically, is just telling us that we're renormalizing lambda by a Bessel function. You can't see that it goes negative, but you look at the absolute value. So one fun possibility this opens up is you can use techniques that are related to this to change the sign of all the terms in the Hamiltonian, which is the same as changing the direction of the flow of time. So there's an interesting possibility of letting a system apparently diffusively expand out and then collect itself back up together again once you reverse the sign of all the terms in the Hamiltonian. That we have tried to do, and it's proven very difficult. We have not made it work, but I think it should work.
So presumably you use some way to get from the units of nanometers to unitless alpha.
Yeah, so it really, 1 over 2 KSA would be the right units, and then KSA is just 2 pi over the lambda of the secondary lattice, which is 915 nanometers in our case. So 450 nanometers or so is like a unit cell here. Yes, and right, we've done that to plot that Bessel function. Yeah, good question.
Now you made the point that thing was showing the absolute value. What would you need to do in order to?
Well, this time reversal experiment,
Phase something
like a negative disorder strength is not as weird as negative tunneling somehow, in my view. But I think the really cool thing to do would be to switch the sign of both of them and watch the thing evolve backwards in time. This I would really like to try again. But, then you have to worry about interactions, which we're not switching the sign of. And maybe you can do some interesting Low-Schmidt echo type experiments. But that would be one way I would think of to really see that that's negative.
How should they think about it? It's related to my previous question, because this is high frequency limit. that you can change the sign of effective sign of tunneling by playing with this modulation. So my new effective Hamiltonian high frequency limit has a negative sign, but the micromotion is the same.
That's right.
So this will be valid over like a short time scale.
So a couple of things to say. One is that it's a high frequency limit compared to the bandwidth, but not compared to the band gap. So you need to choose this like Goldilocks regime of the frequency. And then, yeah, I mean, I think maybe a way of rephrasing your point, which is well taken, is that this Jacobi-Andre expansion is an expansion. There are higher terms in it, which are not zero. So you have to think about how big those terms are and how relevant they are on the timescales of your experiment, I guess.
Sorry. This is a sinusoidal expansion. If I have the luxury, if you have the luxury of appetite,
Oh, yes. Yeah.
then I can actually suppress the higher.
That's right. That's right. Very good point. So there's something called exact dynamical localization. If you use a sinusoidal drive, you don't actually get perfect collapse of the bands to zero, but you can make a actually pretty crazy looking waveform, which is, I think, not even, it's piecewise continuous, but not absolutely continuous, which is optimized to do perfect dynamical localization. The same math is true for the phasonic driving. So you can do funny waveforms and play with that. Yeah, it's a very good point. And an interesting garden to play in, I think. I have a student who's very excited about this and has done a lot of thinking about the different shapes. Okay, so I guess I want to just have a couple minutes at the end to talk about this interactive dynamics idea, because it's, to me, a little bit fun and new. But I do want to say that this is this coherent control of localization is kind of nice, because it really is letting us, I mean, I didn't emphasize it this way, but it's really letting us switch on and off a quantum phase transition by driving. And you might ask yourself, you know, what's the heating here? Is this really working in a reversible way? And the point of this graph is to show that it works pretty well. So if you, I don't want to go through all the graphs here, but if you follow these yellow triangles, you see that the system, if what's happening here is only for the middle range where the triangles are filled with black, am I doing the phase-on modulation? So you can see the system is localized before then. It follows the same curve as an absolutely localized system with only a little bit of expansion due to the projective insertion of the BC. Then it follows a delocalized slope to a good approximation while you're driving and goes back to a perfectly localized slope afterwards. So it's not the case that we're just heating things and shaking things up and everything is becoming garbage. It really does seem to be that we can go back and forth across this phase transition in a controllable way, even in the course of a single experiment. Okay, so, now, right, I forgot. I inserted this slide this morning because this is data that my students sent me just in the last couple of days. And I just want to say, sort of highlight this without claiming that it's anything but preliminary, is that we're talking about two distinct localization mechanisms here. I touched on dynamical localization due to shaking in general in a couple different ways. And of course, disorder-driven localization, Anderson-type localization. And you might ask yourself how those different types of localization interact. And Martin Holthaus and others have explicitly asked this question, and we started to examine it experimentally. I really compliment you guys on your projector. I did not think this effect would show up. So this is data from a few days ago. And what you see here is the modulation amplitude here. So there's a dynamical localization transition at 6.5. Sorry, these are lab units. There's a kilohertz difference between two AOM frequencies. But the dynamical localization transition is here. So you can see, indeed, that looks kind of like it's working. There's blue, not much spreading in that direction. And then the strength of quasi-disorder on the x-axis. And crucially, in between, suppose you have some localization that's partly Anderson-like and partly dynamical, what happens? So this is what happens experimentally. I don't understand all the features of this phase diagram. Some of them, I believe, are not interesting. The yellow at the very top, I'm pretty sure, is a transverse excitation. But some of them, I think, are subtle and interesting. And in particular, I'm curious if anybody has any idea what could give rise to what my students are calling the green brick road in the regime where you have like some significant strength of quasi-disorder and some modulation amplitude that's close to enough to dynamically localize. we haven't thought about it too much because it's just a few days old, but it's kind of interesting to think about what happens in that intermediate regime. So yeah, one axis of this is dynamical localization. The other one is Anderson-like localization. And that's what I'm wondering in the middle there. Okay, so just for the last 5 minutes, I want to talk about a new direction that I'm excited about, and we're building a new experiment on. Our experiment concerns Bose condensates of potassium in reconfigurable arrays of optical tweezers. Originally, we were thinking about this experiment for quantum thermodynamic engines, but now I'm pretty excited about some of these monitored dynamics and interactive dynamics ideas that are floating around. And I think this is going to be a nice platform for investigating some of those. Unless the experimentalists have questions, I'll skip the details of this. That glowing ball is a bunch of potassium at maybe 30 microkelvin. So we're kind of getting there, but we don't have BCs and tweezers yet. And I just want to spend 2 minutes talking about the spiritual goals of this experiment, because I think it's a pretty exciting new direction that a lot of people are thinking about besides us. So I wanted to think about traditional condensed matter physics is understanding some structured quantum system. So if you take wave-like particles and you add a lattice in position space, you get a band structure. If you add some lattice in time, which is to say a periodic drive, you get Floquet matter. But in all these cases, you have your system that does stuff and you measure it to infer what's going on. That describes all the data that I showed you so far in this talk. A little bit of a paradigm shift that's being explored lately is to include the observer as an essential piece of the quantum system that's being observed. And I'm not trying to be sort of, early days of quantum mystical here. But there is some sense that's being understood in a very concrete way lately, and that this actually defines some sort of new approach. And you might call this field quantum interactive matter. I'm not sure who coined that term. It wasn't me. It may possibly have been Vedika Kamani. So this is what I mean by that. So if you think about, block matter, our typical understanding of crystals, you have some periodicity in space and featureless behavior in time. And maybe this is representing a lattice, these connections between the different places in space. You can then add time periodicity to that, and that's a lot of what I have fun doing, having systems that are periodic in space and time, and that's, that was the subject of most of this talk. Recently, people have started thinking about what happens if you add a little bit of measurement into that system. Not complete projective measurement, which is obviously trivial, but just salt it with measurements at a few spots, as indicated here. That's been shown recently. I think I'll say on the next slide some stuff that's been discovered there. And then what I think is really exciting is what happens if you don't take the results of those measurements and just throw them in the trash, but instead use them to feed back to the future parameters of the system. Something which is like banal in the context of classical electronics. Is this a thermostat? Maybe if this is a thermostat, this is doing this, obviously, to control the temperature of this room. But in a quantum system, it's a little funnier thinking about what happens if you have measurement and feedback and stabilization. So to give some of the theoretical context, this is by no means complete, but this is a survey of some of the work done by my theory collaborators, Matthew Fisher and Sagar Vijay, which have shown some of these features of what you might call xenomatter, where frequent observations can freeze the evolution of a quantum state and change the entanglement entropy scaling from volume law to area law. And people are understanding more and more about this and how the character of this new kind of quantum phase transition and the features of the matter that emerges from it. In a lot of fun discussions with Matthew and Sagar and my colleague Andrew Jayich, we've been thinking about what kinds of experimental ingredients would be fun for exploring what I think of as kind of a new regime of condensed matter physics. And so that's part of what we've tried to put into our new potassium tweezer apparatus. Okay, so let me conclude there. I told you a little bit about measuring anomalous localization and multifractality in the kicked Aubry-Andre Harper model. I talked about a coherent control technique by driving a phasonic degree of freedom of a quasicrystal in that same model. And then a little bit about this new apparatus and some of my vague thoughts about a new subfield that's emerging of interactive quantum matter. Thank you guys for your attention, and thank you especially to everyone on this slide.
time for a couple more questions.
Maybe so. So regarding this last part, this interactive matter, I'm wondering if there's a sharp distinction between the Xeno and the interactive matter for the following reason, which is that I could imagine that I have a simplest measurement tool, which is like one spin, which I kind of entangle with my system.
Yeah.
And then that spin interacts further with another piece of the system, and of course has an influence on the feature. And then at a later point, I just measure that and just sort of take it out of the system. So it's not clear, and that feels like the Xeno.
Yeah, I mean, it's not like it doesn't affect the system, the measurement in the Xeno paradigm. Experimentally, I guess the distinction, I'm not sure how meaningful it is I think of like adjusting macroscopic control parameters of the experiment in response to the results of those measurements. So maybe one point to make here is some people hear this and they say, yeah, that's quantum error correction. There's 10,000 papers on this. And that's true. The quantum error correction is an example of this. But what I suspect is that quantum error correction is a corner of a much larger possibility space. Quantum error correction seeks to extend a T1 in some generalized way using this kind of feedback. But are there new phenomena, new states of matter that could emerge by using some kind of structured feedback? I think that's much less well explored.
I think there's also a big theory gulf between the standard open quantum systems methods that work in Xeno and then non-Markov kind of got help you.
It's a bit of a wild west, I think. Yeah.
So I know in many experimental systems, there's like a wide separation in scales between how long it takes to do a measurement and how long it takes to like implement these. It's like these boards.
Yeah.
Is that fine for that in optical batteries?
Yeah, neutral atoms are good from that point of view because everything is so slow. So we all boast, me and Trey and everyone like to boast about how cold our systems are, but that's actually a bug, not a feature. Going along with that is how slow everything evolves. So in a tweezer system, you can do there's no electronics challenges here. The way there might be in a system of solid state spins or superconductors, I think it would still be feasible. And indeed, people have shown with Josephson junction qubits and also trapped ions some early steps along these directions. I think it's strictly easier with neutral atoms than with either of those platforms, just because of the timescales. We don't have to be good at FPGA magic. We can do it. Like we have an Arctic box that will do it no problem, I think.
Combine these two experiments you mentioned with flashback resonance. In particular, you mentioned this idea about flipping the sign of with Miltonians.
Yeah.
Flashback resonance kind of can do that. So there is something about it.
Yes, that would be great. So the unfortunate thing is the experiments I told you about were done with strontium, which is 2-electron atom. Yeah. So it does not have a good flashback resonance. It doesn't really have a magnetic moment. I think it would be really cool to think about transporting it to lithium and changing the sign of the interactions, which we can definitely do in lithium or maybe potassium. So that new experiment I told you about may have some sort of additional possibilities. And the flashback resonance is a very important tool for making tweezer BECs. So a question of whether there'll be lattices in that setup is a little bit still depending on some practical details. But yeah, obviously that would be the nicest thing, to really change the interaction term and do a true like Low-Schmidt echo. And I don't know if that's what's limiting us experimentally right now.
Re-entrant localization, what is the scale that determines the high frequency re-entrant? Is actually physics that causes the re-entrant?
Interesting. So like at what disorder value does it read? Yeah, good question. There are some interesting scales there. Everything I've shown and all the theory that I've done, the relevant scale is like the tunneling energy. So if you go, a few tunneling energies, you see these things. It turns out theoretically, you can explore this much more crisply than we have experimentally. There's a number of lobes of delocalized states that come down and sort of are peninsulas that descend at various values of disorder. And the overall scale there is a tunneling energy, but there's some interesting numerical factors there.
I think we should wrap it up and head to lunch.
Thanks for all the great questions.